Hey guys, so this is our part three of our podcast. This is Adderall's mechanism of action. So here you can see the structure of Adderall here on the left, norepinephrine in the middle here, and dopamine on the right. You can see their similar structures here. Um, so based on this, you can see the similar ring structure and that Adderall itself has very similar effects to these neurotransmitters.
So Adderall basically works on increasing levels of dopamine and norepinephrine mainly. It has some effect on serotonin, but only moderately from experiments. So we can basically predict the effects of the drug based on the effects of these neurotransmitters. So if you're going to increase dopamine, you're going to have euphoria. Norepinephrine, you're going to increase alertness. You're going to increase heart rate, attention. Dopamine, you're going to have more pleasurable things. Serotonin, you're going to feel happier. You're going to have different changes in sleep cycle, changes in eating patterns as well. So both the active ingredients of Adderall work in the same way, although they have different potencies. So they basically bind to the same biological targets, but the potency is different. Amphetamine, there's different. So basically, Adderall is a combination of four different types of amphetamine, and it's 25% each. So there's 25% amphetamine aspartate, monohydrate, amphetamine sulfate, dextroamphetamine saccharate, and dextroamphetamine sulfate. And these all these chemicals compose Adderall, and they're the exact same almost, except there's different potencies for different things, but they do the exact same thing.
So for routes of administration, so the most common form for taking Adderall would be orally. On this diagram on the right here, you can see it would first be digested by the individual. And it's metabolized in their liver before being absorbed into their bloodstream. Adderall XR and SR stands for slow and sustained release of the drug. So in this picture down here, you can see a picture of an XR, so extended release, and it's a common dose right here, 25 milligrams. Another less common approach would be transdermal. This is also a slower release compared to these three down here. So sublingual, which is under the tongue, and under the tongue there's a lot of blood vessels, so it's quicker, it absorbs the drug more quickly here. Rectal administration and insufflation as well. So these routes they act faster, so the drug is more effective, I would say.
Okay, so now we're going to talk about absorption of Adderall. So Adderall is a weak base. It has a pK of 9.9. So basically, when the drug's ionized in the digestive tract, it slows its rate of absorption. Adderall immediate release reaches peak plasma levels within 1.5 to 2 hours of administration, whereas extended release gives an immediate bolus, so an immediate dose, and then it has a delayed dose following 4 hours later. And the slower release of the drug allows it not to create spikes in plasma levels, so you're not having basically you're having a slower constant release of the drug as opposed to spiking the drug up in the blood and then having it drop down and then doing that again. This drug's very liquid soluble as well, so it needs to travel through the blood-brain barrier. So again, this picture down here will review a bit of the blood-brain barrier. So again, it's very tightly fenestrated. There's tight gap junctions, and for it to cross through, it has to be lipid soluble, which Adderall is. This graph up here compares some absorption rates of different ADHD medications. So in the blue is Adderall extended release. Again, comparing it to the red, which is Vyvanse, which is another ADHD medication. They basically have the same kind of spike in their, once you take them, it takes about 2 hours for it to have peak levels. And then Adderall typically drops off quicker than other ADHD medications. So oftentimes it's beneficial to have that extended release, so where it has sustained levels over time, because Adderall, again, it drops off. You can see here within 5 hours, it's already lower than the Vyvanse or Concerta, other ADHD medications. So here we're going to talk about the metabolic pathways of Adderall. So again, the active ingredient in Adderall is amphetamine. Amphetamine is broken down by the CYP2D6 enzyme, and this from there it goes to 4-hydroxyamphetamine, which are there. It'll be this enzyme here. It's called beta hydroxylase, and this makes it into 4-hydroxynorepinephrine. Another metabolite, so CYP2D6 again gets broken by another enzyme. It's called DBH, and this gets broken down to norepinephrine, which then will be broken down again by hydroxylation and by the CYP2D6, which is where this arrow is. So this cascade also, amphetamine is also broken down by oxidation of an enzyme called FMO3 into phenylacetone. And phenylacetone is also oxidized into benzoic acid, where then it goes to, it's conjugated into hipporic acid, and as well, phenylacetone is also hydroxylated into this compound right here. And this just is the metabolic pathway of Adderall. Again, it's somewhat confusing, but here in these arrows, there's enzymes and everything is kind of getting cleaved off or added to make it easier to be excreted. So,
All right, so I'm going to talk to you guys about the elimination of the drug from the body. So generally, this depends on the pH level of the of urine. So low pH in urine, the metabolite won't be reabsorbed into the kidney, and it will increase excretion. Um, Low pH not reabsorbed in kidney, well, while in the urine increases excretion, so decrease half-life to approximately 7 hours, so the drug will be in the system less because it is being excreted. Um, High pH, so prolongs half-life, causing decrease and excretion. So the higher the pH, this decreases excretion, so this would increase the time the drug is in the system. Approximately 40% excreted unchanged by the liver. So 40% is not metabolized, but it is still excreted as just straight Adderall.
so now we're going to talk a bit about Adderall's mechanism, and it's somewhat complicated. So once Adderall is broken down to its main component, which is amphetamine, this crosses the presynaptic barrier through the dopamine transporter. So basically, it works against the concentration gradient and goes in through the transporter, as opposed to another way around. Once amphetamine is inside the cell, it's very affinitive to the VMAT2. This is a vascular monoamine transport 2. So basically, it's taken up and it's packaged in vesicles. And basically, this VMAT2 is responsible for packaging monoamines and such as dopamine and norepinephrine, and it's causing their release into the cleft. So this high affinity to the VMAT transport proteins, transport of monoamines into the vesicles causes a buildup of neurotransmitter on the axon terminal. So basically, this stops the package of the monoamines when amphetamine binds to the VMAT2, and it causes buildup of neurotransmitter at the axon terminal. So amphetamines also change the pH, which causes the reversal of the VMAT again, which causes it to become leaky and therefore cause a release of neurotransmitter closer to the synaptic terminal. Another mechanism, the way amphetamines work, is they cause a reverse action of the serotonin reuptake transporter, so SERT, norepinephrine transporter, NET, and then the dopamine one is DAT pumps. So typically these pumps work in causing a reuptake of the monoamines from the synaptic cleft back into the presynaptic neuron. So these are inhibited. So basically what happens is the monoamines can't be recycled, and there's more of these neurotransmitters present inside the synaptic cleft. So instead of reuptake, they actually do the opposite. So they take the monoamine and they almost shoot it out the transporter. So they take it from the presynaptic neuron and they basically shovel it out. And this is caused by sodium entering the cell with amphetamine. So whenever one molecule of amphetamine goes in, there's usually two molecules of sodium that move in, and this changes the ion gradient, which causes an insufficiency in reuptake. So the neuron can't recycle its monoamines, and they have an increased concentration in the synaptic junction. Another way this drug works is inhibits MAO, so monoamine oxidase. So this metabolism or enzyme is responsible for breaking down monoamines, such as dopamine and norepinephrine. So when this is inhibited, there's going to be an increased level of these neurotransmitters because the enzyme isn't there to break them down. And this overall, its simplest form is this drug will increase the levels of monoamine, specifically dopamine, norepinephrine, somewhat serotonin, in the synaptic cleft, and this will have an increased effect based upon these neurotransmitter profiles. So here on the left, we have a bit of a picture of what happens at the specific neuron. So here in the blue, we have amphetamine, and they basically diffuse across the membrane through the dopamine, the DAT transporter. And what they do is they inhibit this VMAT2, the synaptic vascular membrane packaging. So what happens is this is inhibited. So there's increased dopamine and norepinephrine, which is pumped out of this transporter, and it's like kind of laying at this little area at the synaptic junction. Another mechanism, what happens is it causes competitive reuptake inhibition. So what happens, this little this dopamine transporter here, the DAT, usually what happens is it takes dopamine from the synaptic cleft and it recycles it back into the presynaptic neuron. Well, instead, it does the opposite. It takes this drug, this neurotransmitter, and it pumps it out. So it's almost working in the reverse action. So this is going to increase the amount of dopamine and monoamines in the synaptic cleft. Another action it does as well here is it decreases the amount of monoamine oxidase. So what will happen is monoamine oxidase would decrease the levels of monoamines in the synaptic junction. So when you inhibit this enzyme, you're basically inhibiting the breakdown of these monoamines. And you're going to have an increased level of dopamine or epinephrine in this junction. It's going to be able to fire and meet its receptors on the postsynaptic neuron. So again, we went over this many times. This is the brain on Adderall. It's more metabolically active. And this is the brain without Adderall as well. So we're going to go over some ways at which areas that the brain is affected. So over time, again, the researchers have done that the damage of amphetamine use, it affects many areas, memory and emotion and reward. So areas caused in emotion, so the limbic system, the amygdala as well, the hippocampus. So you're going to have some decreased memory loss. You're going to have some loss in the frontal lobes as well, maybe possibly in the back area of the brain here as well. So this is the area basically of, we're going to focus more on dopamine because that's the primary neurotransmitter that's affected by Adderall. So again, the dopamine starts at the VTA. It has projections to nucleus accumbens and the frontal cortex. So these projections, they're responsible for reward, motivation, pleasure, euphoria, convulsions, motor function. So again, when this area is stimulated, you're going to have an increase in these functions. Here's serotonin, moderately affected. Cut starts in the raphe nuclei and goes projects all throughout the brain, and through the cerebrum. And the serotonin is responsible for the mood, memory, processing, sleep, and cognition as well. Again, this also has responsible for addiction potential. So whenever you're increasing the levels of dopamine, which this drug does, you're increasing the addiction potential of the drug. So there's going to be more pleasure, and eventually the brain is going to crave or need that motivation which this drug causes, basically due from that release of dopamine from the VTA and the nucleus accumbens there.
Okay.
So this concludes our podcast 3 on Adderall's effects on the body and its mechanism of action. Thank you for watching.